Hi everyone. So today, we are going to be going over um an introduction to OpenMP. So for those who have not heard of OpenMP, you'll be able to like learn more about like this kind of parallel programming, which is a bit different from what GPU programming is like, or like how MPI programming is like. So the agenda for today, first we are going to go over different parallel programming models. Then we are going to go over OpenMP. We are going to go over OpenMP's core syntax, and there will be like an example hello world. Finally, there we'll be going over some more like some basics of OpenMP parallel programming, such as thread creation, synchronization, and parallel loops. And throughout this entire mini workshop, there will be some example code which will allow you like maybe even if you can't run it right now because you don't have access to Pace, you'll be able to go back home and study up on the syntax of it. So just an introduction to parallel programming models, what they are. So essentially with parallel programming, while there's a lot of shared themes, um, such as, the algorithm design aspects of it, there are different ways to do parallel programming depending on what kind of machine we are trying to program. So the first one is shared memory model, in which basically multiple threads will access the same memory space. Then there's a message passing model, which is that multiple independent processors will communicate with each other by sending messages. There's a data parallel model, otherwise known as SIMD, which is when operations are performed on multiple data elements simultaneously. There's task parallel model, or also known as functional parallelism, which means that workload is divided into different tasks, which are then distributed across processors. There's a single programmable data model, or SBMD, in which a single application runs on multiple nodes, and each node will execute the same code on different data subsets. And finally, there's a hybrid model, which basically combines multiple models all together. So for example, you can use the shared memory model and message passing model together. So today, we'll be going over the shared memory model, which is what OpenMP enables. In our past workshops, we have gone over message passing in our MPI workshop, and there's like the data parallel model in the CUDA workshop. So if you guys want to check those out, you know, that's in our other workshops. So what is OpenMP? OpenMP is essentially an API for writing multi-threaded applications. It provides a set of compiler directives to do this, which compiler directives think of this as suggestions to the compiler that the compiler will mostly follow. So people who are more familiar with C and with C programming, you'll be familiar with compiler directives. People who are more familiar with Python, you might not be as familiar with this kind of concept, but we'll walk through some sample code to get you more familiar with this. Um, so what are some alternatives to OpenMP? OpenMP is not the only way to do sort of parallel programming on the thread level or like shared memory program model programming. So there's also something called the Intel thread building blocks. Um, and the advantage is that it offers a cleaner, more abstract programming style for new projects, but the disadvantage is that it requires more significant program redesign. There's P threads, which a lot of people will be familiar with. Essentially, the advantage is that it provides fine-grained control, but the disadvantage is it's complex to use because it requires manual thread management. For those who have done that, you know what I mean. There's the C++11 and above threads, which provides a more portable and type-safe version of thread management than P threads, but also it does require manual thread management. There's also something called Silk, which not a lot of people might know. This is mostly popular in an academic context, but essentially why it's good in academia is because it does provide an efficient task scheduler, more efficient than OpenMP. But the disadvantage is also that it does require more significant programming design for certain applications. Finally, there's system calls, such as fork, join, etc. An advantage of this is that it runs programs in separate address spaces by default, but the disadvantage is that it runs programs in separate address spaces by default if you want to do true shared memory programming. So that means like in order to do shared memory model programming, you do need to like set this up manually. So what is some core syntax of OpenMP? So first, to use OpenMP, function prototypes and types must be included. So in C or C++, for example, you do this with include omp.h. Um, and then in Fortran, we just include this for reference. We'll use basically this line, use intrinsic omp lib. And then most constructs are, as I said before, implemented through compiler directives. So compiler directives in C and C++ looks like this. Basically, we have like this hash symbol, and then and then there's pragma, marking this as the pragma compiler directive. And then essentially it's followed by pragma OMP parallel num threads, like an example of this. So mostly OMP compiler directives will be pragma OMP something. And then for Fortran, compiler directives is basically an exclamation mark and a dollar sign and OMP. So C++ also allows formation of constructs through attributes. Instead, this is something that we will not be using in this workshop because we'll be using C, but this is just included here for reference. So what exactly is OpenMP construct? So OpenMP constructs is made up of directive names and clauses and a structured block. So what the star sign means essentially means that it can be included or not. And then the as within the parentheses just means that there can be multiple of them. But basically OpenMP constructs always need at least one directive name. What is a structured block? A structured block is essentially a block of more than one statement with one point of entry at the top and one point of exit at the bottom. And most OpenMP constructs will apply to a structured block. A directive name is a specific action or behavior that will be applied to a structured block. And clauses will are basically things that modify action or behavior to customize how the directive is executed. So here are some example OpenMP constructs. What the pink highlights are here for, these are essentially the directive names. So you can see like these are sort of the behavior that we expect. And the blue highlights here are the clauses. So you can see that essentially this is more like how we want these these directives to behave. So question one might be like which of the following parts of this OpenMP constructs are clauses? Um, someone just feel free to answer because we have so few people. Yeah. Yeah. Yeah, essentially the clauses are stuff that describes the behavior we want the directive to take. So these are all examples of a clauses. These are actual clauses. We will not be describing everything, but yeah. So yeah, this is an example hello world that we sort of have. essentially you can see that we have something we have like we have a construct here, pragma OMP parallel. There is a pair of open braces which sort of mark where is the structured block. So the structured block consists of lines 8 and 9. As you can see, there's one entry and one exit. Um, and yeah, let's see how it behaves. So in order to sort of run our programs, um, we first want to allocate one node that can run 8 threads in parallel. And then you can type make here. This will basically compile every single program that we have written. And then you can run the program here. So essentially you can see like we are printing so hello from each thread. One thing that you might note in particular is that the thread numbers are actually not ordered. And this is like a key feature of multi-threaded programming. And this does bring in some concerns that we do need to consider later on when we are doing some of our programming. Yeah. And then now we'll be going over thread creation. So OpenMP uses fork join parallelism. And what this means is essentially like a parent thread will spawn a team of child threads as needed. So an advantage of this is basically that parallelism can be added incrementally rather than requiring an entire overhaul of a code base. So you can see here that essentially there is like this parent thread that goes like this. These horizontal regions essentially mark where serial code is executed. And yeah, there are parallel regions sort of interspersed with different number of threads. You can set the number of threads for each parallel regions. It doesn't have to be entire team of parallel threads. And so parallel regions are created using the parallel construct. So that's the pragma OMP parallel. And each thread will execute a copy of the code within the structured block. There's also OpenMP functions that can be used to access important information or functionality within a parallel region. For example, there is a OpenMP function, OMP get thread num, which is used in some of the following examples. This gets the thread ID. Yeah. And then there's also shared versus private variables that we need to go over. So shared variables are variables that only exist in a single memory location that is accessible to by all threads. Private variables mean that each thread in the team creates its own local copy of a variable. Normally, variables declared prior to a parallel region are shared variables, while those that are declared within the parallel region are private variables. And also you can use the shared and private clauses within the parallel construct in order to declare specific variables parallel or shared, private or shared. Um, yeah. So one question then might be, so given the following serial program, which lines should be made into a parallel region based on what we have said? So essentially this would be like a first step towards designing a parallel program. You want to decide which code is actually parallelizable. Yeah. Mm, so 6 to 14. Well, it's more like 8 to 12. Yes. Mm-hmm. Oh, okay. Yeah, I guess I should make this a bit brighter. Mm-hmm. Yeah. And also, a follow-up question. This is the exact same program, but which variables should be made private when you're parallelizing this program? So you don't want this variable to be shared. X, okay. And then, so there's X and I. So you'll notice that essentially each thread will want to sort of go over like their own indices. So X and I would be the private variables. We have implemented a serial version of a program and a parallel version of a program. So the serial version of program is like the exact same. So we'll run it here. So you can see, except for the timing part, it's exact same. I can't type. So basically, I'll clear this so it becomes better. But yeah, you can see like that is the runtime. The value of pi is basically sort of what you expect. Just look at the first two. It's like 3.14. That's the value of pi. And then there's a parallel version. And so yeah, essentially the same value of pi, but with serial program, you can see that it takes like 0.334 seconds, while with the parallel version, you essentially only take 0.002. So you can see like there is quite a marked speed up, even with something that with like a simple program like this. Yeah. Oh, wait. Me? Okay.
So the next kind of topic that we're going to talk about is synchronization. Often you can think about like one single kind of like variable being acted upon and how that could cause problems. And so, yeah, essentially it's when multiple threads access shared memory, we need synchronization to avoid incorrect behavior. And when we say incorrect behavior, that's mainly race conditions, which we've kind of like gone over race conditions in other workshops and presentations, but I'll just do like a quick kind of overview of it again. So a race condition happens when two or more threads try to access the same memory location and there's no coordination. So you kind of end up with something with like mismatched information and you end up with an incorrect kind of like overall value at the end of it all. So an example of this is just a simple counter. If you try and kind of like go through that, you might end up with like some errant values. And the problem is that counter itself is not kind of its own atomic action. And multiple threads act on it at the same time, which is kind of like really the biggest problem. So I think we do have a example of the race condition code. So let me just comment out everything else before that or after that. So E and dot slash synchronization. That still is showing everything, which we didn't want, but that's okay. Oh, oh, you're right.
You still haven't saved it.
Oh, yeah, I'm stupid. Sorry, my bad. All right. Yeah. So if we run this, let's clear this and run this again. We basically see that we get an extremely crazy value that's not, we expect a million and we get 291,000, which is definitely not what we want. And that's because multiple things are trying to act upon the same kind of value at the same time. Um, and so, yeah, so there's essentially a bunch of constructs that you can use to kind of get around this, but each of those have their own pros and cons. There are quite a few more than what we're going to go over today, but these are just like a subset of some of the kind of important ones for certain cases. So the big one big one that you start off with is critical. So critical only allows one thread to enter into like a block of code at a time. And this works for things when you have things put together and everything is kind of working on one thread. Like when we think of like that parallel, that fork join parallelism, when we're in that middle portion where it's serial, this is kind of good. But yeah, the main problem with this is it typically really just serializes the program. And so yeah, that's kind of the problem with it. And it's not very fast either. So like if I uncomment this code and make again, yeah, I know I keep forgetting to do that. Make again and then run again. We see that we get the correct answer, but it takes 0.6 seconds, which, kind of, I think we can do a little better with some of the other constructs that we have available to us. So the next one is atomics, which it really just focuses on one memory location. So in this case, it's our one variable. Um, and so the pros are it's lighter, but the cons are you can only really use it for a simple thing like an increment. Um, and so one atomic update at a time, it's kind of not really the best thing for like large scale operations. And so, but for this case where we're just summing a counter up, um, it's kind of a decent option. So. So yeah, we see considerable speed up from critical to atomic, but really like I think the crux of kind of this um the speed up over here is using the reduction construct. And so this is really like where you're parallelizing and taking advantage of the parallel, like the multiple threads. So each thread gets a private copy of the variable, and OpenMP combines all of those safely at the very end. And it's faster than both critical and atomic for counting and summing operations, but there are still cases where you might want to use critical. There are still cases where you might want to use atomic. So it's really like limited to when you're kind of compiling down to one singular value and you want to parallelize that process. So if we kind of look at reduction and we uncomment this and make this, and let's just clear this and run this. Yeah, we see considerable speed up even over atomic counting. So that's kind of, one, that's kind of like I guess kind of three ways you can do the same thing, but um yeah. So I think one way to look at it is atomic is narrower and cheaper for like simple updates. But critical is like the easiest way to kind of like fix something. Like if you're having race conditions popping up, critical wrap critical block around it and it'll take care of it. But you are losing that speed up. Which kind of like it's like why are you using OpenMP at that point? So you got to be like kind of smart about where you use that. So yeah, I have a question here, which is kind of just on this question. When is atomic usually preferred over critical? So yeah, I'll leave that to you guys. Just keep in mind, atomic is like for very like mundane, simple operations. B, yeah. So it's B. Because you're really just like focusing on that one counter variable, taking to our example. Um, and yeah, that's kind of where that is. So there's two more constructs. These are kind of like um, a little bit, I guess, like it's ways of separating out different portions of code or different pieces of logic, so to say. So the first one is barrier, and the actually these two constructs, barrier and single, can be used pretty well in conjunction. But single's kind of a separate thing. So barriers are good for synchronizing different phases of your code. So let's say you have like one phase where you want to have some set of, thread work and then serialize, and then another phase, um, just like how we were seeing in fork join parallelism, that's where you kind of use something like a barrier. And so it's really like when the next parallel phase depends on the previous parallel phase. So phase n depends on phase n minus one. that's kind of like where you would use a barrier. So barriers coordinate progress, but they don't protect any of the problems that might pop up. You still have to be cognizant of that within kind of a phased piece of code. Um, and so, yeah, kind of use a compiler directive the same way you would that over there. Um, Single is, you have everything operating on one single thread. So you might use this for things like logs. You might use this for things like metadata, like kind of like one compiled or one single operation. So if taking it back to fork join parallelism again, you'd have your barrier code, and then within that, you'd have whatever parallelization stuff you're doing. And then after that, you'd like kind of like use single to kind of maybe do some things with it, and then so on and so forth. Um, so yeah, have a piece of code to show on that too. So it's the last one. And just taking a look at the code, you kind of see like it's that same aspect of going through every thread. And you have a barrier here, and then you have a single directive here. And so yeah, if we kind of make this and run this. So yeah, so you see like every thread goes through phase one, and then barrier's done. It's a single thread saying all threads completed phase one. So that's one way to know like, okay, that kind of like branch out parallelization process or set of processes is done. And then you kind of start off again. And so yeah, I think it's like a pretty nice way to kind of, it's like good constructs for you to um like when you're thinking like I guess in terms of parallelization, it's good to kind of know that these things exist. Otherwise you might just end up have running into race conditions all the time. Um, so yeah, so what does pragma barrier do? So think back to fork join parallelism. Um, See, yeah. So it forces all threads to wait until every thread reaches that point. So in a sense, it's kind of like goes through every single thread and does whatever it needs to do there. Um, so yeah, I mean, this is just a subset of the tools. There are a lot more, but if you're writing to separate things, you're not really going to need synchronization. Um, but if it's like a shared counter, the best thing to use is probably a reduction, just because you're kind of like able to actually parallelize out the load. If it's a simple shared increment, you'll probably use an atomic. If it's more complex shared logic where you kind of like need to have multiple lines of code, then you'll use critical. But remembering that that also tends to serialize the code. And if you need all threads to finish in a certain portion before another portion, you would use a barrier. And then if you need one thread to do something altogether, maybe in between your barriers, you would use a single plus. So yeah, correct synchronization means you're protecting kind of like where things are shared. You want to make sure you always use the lightest tool because as you can see, like if you use critical for the wrong thing, you're just adding unnecessary time. Versus like if it's very simple and you can use atomic, you're saving time versus if you're able to kind of use a reduction, saving the most time. And prefer redesigning around private data when possible. So yeah, I think that's kind of everything on synchronization. Pass it back to you.
Um, yeah, so we'll continue with talking about parallel loops. So before we have introduced parallel constructs, which we know now that it allows multiple threads to each execute the same code. But what if we want to have each thread execute different pathways of a code? This is something called work sharing, and OpenMP allows different kinds of work sharing. So there's loop work sharing, section work sharing, task work sharing. In today's workshop, we'll be going over loop work sharing mostly. So what is the loop work sharing construct? You essentially declare it using Pragma OMP4. Um, and if essentially what it means is like in a parallel region, each thread will execute a different iteration of the loop. The syntax for loop work sharing is essentially this. First, you need to mark this as a parallel region with pragma OMP parallel. Without this, basically every iteration will be running on a single thread. So there will be no parallelization. Then you mark the loop as a work sharing construct using pragma OMP4. You can also condense this into like a single line pragma OMP parallel for this. Both of these behave the exact same. Um, with parallel loops, what you need to be aware of is that it has some restrictions. Essentially, this is because the way that OpenMP paralyzes, it paralyzes things during compile time. Basically because it is using compiler directives to sort of paralyze things. So that means that OpenMP needs to be able to determine the number of iterations beforehand. So what does this mean? This means we cannot have any breaks, exits, returns, or anything else that can change the number of iterations during runtime. This also means that the index update has to be predictable, which most of the time means that it has to be incremented or decremented by a fixed amount. And finally, this means that no changes to a loop index inside the loop are allowed. So what this means is, for example, suppose we have index loop I, we cannot suddenly in runtime decide to do I plus 2 instead of I plus 1, etc. So yeah, there are some restrictions to parallel loops with OpenMP. And also, when parallelizing loops, you need to make sure that loop iterations are independent of one another to avoid race conditions. So essentially what this means is that um yeah, like basically loop variables within the loop cannot be dependent on the previous value of that variable. Um so one question would be which of these loops have loop iterations which are not independent? So these are the loops that cannot be parallelized by OpenMP, like at least naively. Like you can't just put something in front pragma OMP parallel and make parallel 4 and expect it to work properly. Hmm? Yeah,
Definitely the bottom.
bottom left is not parallelizable. And then just another hint, there's another one. So based on, so this is correct. So what would be the other one that is not parallelizable? Top right, yes, that is correct. So these two, essentially, their loop iterations are not independent. So you might be asking why that is. So for example, in this case, you see that AI essentially depends on the previous value, AI minus 1. So what this means is basically each iteration of a loop cannot actually execute in parallel. If it does that, that means the value of AI would not necessarily be the correct one. Um, so like a follow-up question for the bottom left one here is, which of these loops are not parallelizable? So notice that there's actually two loops. So are both of these loops not parallelizable, or is it just one of them? What do you guys think? Yes. So essentially, only the inner loop is not parallelizable. This is because you see that essentially only J depends on the previous iteration of J, right? You can actually parallelize every single iteration of I with no problems. Yeah. Um, but essentially by default, the loop work sharing construct parallelizes only the outermost layer of the loop. Um, in order to actually like parallelize every single iteration, like every single level of a loop, you want to use something like collapse. So in this case, we're marking this as collapsing, paralyzing the first layer of the loop. So collapse one means paralyze the first layer. That basically means that we can just get rid of this and this doesn't matter. You can also do paralyze collapse two, which means that we'll be paralyzing both the I and K loops. And finally, there's collapse 3, which will be paralyzing all three loops. So yeah, here's a demo for this one. So first, there's a matrix multiplication demo. So we'll run this like this. Essentially what this demo does is it compares the runtime between like parallelizing only a single outer loop versus a serial implementation of matrix multiplication. So what you can see is with 1024 matrix 1024 by 1024 matrix, the matmul execution time is much slower. Parallel matmul execution time is much slower than the serial version. And then now we'll one question is parallelizing all levels of a nested loop always more efficient? What do you guys think? So for example, is parallelizing only the outer loop always going to be less efficient than parallelizing all three loops, for example? No. Okay. Yeah. So no would be the correct answer. And yeah, like essentially we can run our other matmul example. Uh, So essentially what this does is first we parallelize only the outermost loop, and then we parallelize the two outermost, and then finally we parallelize all three loops. So you can see here, like essentially like when we parallelize one loop and two loops, like we actually get better performance than when we parallelize three loops. And if it's not as convincing, we can run it again, and we'll yeah sort of always see this pattern. Um, and essentially why this is because of the thread overhead, the thread creation and launching overhead. So yeah, like with this, the difference is even larger. Essentially, like when we try to launch too many threads at once, it is quite a huge overhead for the computer, and yeah. So we don't always want to create so many threads to handle all the computation we want. Sometimes it is cheaper to just do computation on one single thread. So yeah, in conclusion, so these are some things that we want you guys to take away. So OpenMP provides an easy way to parallelize programs with small changes to the code structure incrementally. OpenMP constructs is made up like basically three parts. Threads are created with a parallel construct. Synchronization is required to prevent race conditions when modifying shared memory. And finally, launching more threads does not always equal faster for performance. Yeah. So thank you guys for coming. If you haven't yet, please fill out the attendance. It would really help us a lot. And yeah, if you have any questions, please reach out to the curriculum officers or anyone else. Um,